final discussion of sigma notation, there are a few rules that might be useful to know, but I wouldn't spend a ton of time memorizing them with regards to certain types of rules. So if we have a summation of a constant, then the sum will always be, as long as it's going from 1 to n, the number of terms times the constant itself. And you can make an adjustment if you're not starting at 1, if you'll think about it for a moment. The second rule is if we're going from 1 to n and the rule is just I, then our sum is always n times n plus 1 divided by 2. Third one is if our summation is going from 1 to n of I squared, then the summation is always n times n plus 1 times 2n plus 1. And all of that is being divided by 6. And finally, if we're looking at the rule that's I cubed, then the summation is always n squared times n plus 1 squared over 4. And if you're real curious, you can find the proofs for these. They're kind of unnecessary for our concerns right now. But they aren't difficult. So if we apply these, let's consider the sum as I goes from 1 to 45 of 3i. And we know this is equal to 3 times the sum as I goes from 1 to 45 of just I. And we know that the sum from 1 to 45 of just I is equal to n, which is 45, times n plus 1, which in this case is 46, divided by 2. So when we take that whole thing and multiply it by 3, we'll find the sum from the beginning, and this ends up being 3,105. Our second of 6 examples that we'll do here in part 3, as I goes from 1 to 30 of I squared. Well, if we consider our rule for I squared, this will end up being 30 times 31 times 2 times 30 is 60, plus 1 is 61, and all of that will be divided by 6. So following that rule, our sum is 9,455. Our third summation problem, as I goes from 1 to 90 of the rule 2i squared minus 1. I'm going to break this up in a lot of different ways. So this is equal to 2 times the sum as I goes from 1. Looks like it's 50, so I'm going to change it. The original problem was 50. Of I squared minus the sum as I goes from 1 to 50 of just 1. Well, this first sum will be 2, and I squared, as we know, will be n, so 50 times 51 times 101, all divided by 6. And this will be minus 1 times 50, or just 50. When we simplify this, we end up with a sum of 85,800. We've got 3 more sums to do. Here we have the sum as I goes from 1 to 60 of I squared minus 4i plus 2, and hopefully you can see why we would not want to have to deal with this in a lot of different ways. We know that the sum of by writing out every term. So we know that the sum of I squared will be, in this case, 60 times 61 times 121 divided by 6, so that represents I squared, minus 4I, well that will be negative 4 times, and the sum of just I will be 60 times 61 over 2, so there's minus 4I, and the sum of just 2 will be 2 times 60. So by using all of our rules, we can figure out that the sum is 66,000. For our fifth problem, we're looking at the sum as I goes from 1 to 38 of 3I minus 5 squared. And this one's a little bit different. It doesn't exactly fit any of our rules per se, but if we were to expand this first, we could consider 9I squared minus 30I plus 25. And so 9I squared will end up being 9 times, since we're going to 38, it'll be 38 times 39 times, what was that, 60, 77 over 6. And minus 30I will be negative 30 times, and we know the sum of I is 38 times 39 over 2. And finally, we've got plus 25, so that'll be plus 25 times 38. And so using our calculator to help speed this up, we will find that the sum is 149,891. And for our last summation problem example, let's consider the sum as I goes from 1 to 20 of I cubed minus I squared plus 1 plus I. And again, I would not want to have to write every term out. We know that the sum of just I cubed will be n squared, so in this case that'll be 400 times 21 squared, which is 441, and that needs to be divided by 4, minus I squared, so I squared in this case is 40 times 41 times 81 divided by 6, plus I, and I in this case will be 40 times 41 over 2. It looks like we could do a decent amount of factoring here, but I'll just let my calculator help me. 22,780. So there we have a bunch of summation examples, and I hope this helped.